Okay, thank you. All right. Welcome, everybody. Thank you for coming to today's seminar. It's a pleasure to have here today Dr. Svetlana Bachman from the National Severe Storm Laboratory at University of Oklahoma. And Dr. Bachman is actually grew up in Russia, and she's from actually Pennsylvania Technical University is your latest affiliation in Russia, and then she got her master's degree and PhD degree in electrical engineering from University of Oklahoma, and she's now associated with the Cooperative Institute for Mesoscale Meteorological Studies, and affiliated with the University of Oklahoma as well. And it's a pleasure to have you here. She'll be talking to us about weather radar, which is very relevant in this part of the country. And thank you for coming, and the floor is yours.
Dr. Prince, thank you for introduction. So let me start. You can stop me at any time if you have any questions. I'll try to go slow. I'll try to cover 3 topics, but if we run out of time, we don't have to go in all 3 of those. Weather radar signal processing, and we will talk about spectral processing. First, I'll give you an outline. So again, I will give you a brief background, then I'll describe ground clutter filtering. I'll present a new methodology for ground clutter filtering. Then I'll talk about a different approach in spectral analysis, which will be about biological scatterers contamination. And the last topic I will try to cover will be range and velocity ambiguity. How can we deal with that, and what kind of spectral analysis can we use to solve the problems which I will present. In the background, I will tell you, well, what a radar display is, so we all on the same page. Give you some facts which we need to keep in mind when we're dealing with the weather radar. I present you the weather radar prototypes, which I will use to obtain data which I process and show you in this talk. Because it's important in dealing with signals to know where the signal comes from, I will brief you on the weather radar signal sampling. And then when we know what the signals are, then I can present to you the spectral analysis, the weather radar Doppler spectrum, and how the moments are obtained. So radar display. When we turn on TV, what we see is not really a radar display. That is a radar product, which is a product after we obtain the radar moments, and then we apply models and compute something, and then we turn on TV and we see here's rain, here's ice, here's what we're going to expect to see. If you go to one of these websites, like here, oops, you would see the real radar display of velocity, is it shown here? And I'm having problems here. And display of reflectivity. The things to keep in mind is that radar is in the middle of this picture. The range extends away from the radar, so we have range circles. Azimuth angle, there is a concept. So 0 degrees pointing north, 90 degrees is east, and so on. One radial is generally echoes from one radar beam. And here I highlight it so we can all see what it is. One range location is the same as one resolution volume. And this echoes from one volume in particular, which will be represented as 1 pixel on the radar display. So there are several facts we need to keep in mind when we deal with the weather radar data. First one, most of weather radar are 10 centimeters. There are 3 centimeters wavelength radars. I will not talk about them. For the 10 centimeters weather radar, targets are assumed to be 10 times smaller than the wavelength. It's about 1 centimeter. Therefore, when we have different targets which are larger, which are birds, airplanes. So this is a bad situation. So we don't want that. One resolution volume is assumed to be uniformly filled with scatters. So when the volume is not completely filled, this is again bad situation. So keep it in mind. Radar beam. Radar beam has side lobes. When we deal with the weather returns, we assume that the returns from side lobes are very small. So if there are returns from side lobes, again, we have a bad situation. Now, pulse volume. Because the radar beam extends at far ranges, the pulse volume is different close to the radar and far away from the radar. If we're looking at a storm, which is the same size, closer to the radar, it will appear big on the radar display. Now, there can be returns from multiple reflections. So we need to keep in mind that scenario too. There also can be shielding of the radar beam. There can be blocking. There can be attenuation. So another things to keep in mind. There are lots of things to keep in mind. And the most important, I think, is we never know how our radar beam propagates. There can be subrefraction, refraction, superrefraction, or ducting. So all these beams are valid, and we never know what really happens. But we have to keep it in mind. Okay? Next, I will present the weather radar prototypes, or the tools at which I'm looking at the weather. And here is the picture of two radars. One is called NWRT, which is National Weather Radar Testbed. Another one is KUN, which is Weather Surveillance Radar 1988 Doppler, which is WSR88D. This radar has dual polarization. What is special about this radar? Here, that it is a prototype of all the radars which are operated by the National Weather Service. So all these images which you obtain from the TV to see the Doppler, they come from those radars.
Where
WSR88D.
Where are they located?
There are about 150 locations. They are located all over the country. I do not have a map with these radars. Yes?
Are all operational radars dual polarized?
So the question is, are all operational radars dual polarized? No. This is the prototype. It has dual polarization. There are several more radars which have dual polarization. What is going to happen in the future, in a couple of years, many radars in the network will be upgraded to dual polarization. So this is technology that is coming to be around us and with us. Does this answer your question? So, here are some parameters of the radars. NWRT has a phased array, passive phased array antenna. It's electronically steerable radar. The KUN has a parabolic dish. It's mechanically steerable radar. So this is conceptual difference. The frequencies of these radars are similar. Those are both S-band radars, meaning that they have 10 centimeter wavelength or about 10 centimeters. And so I just want to show you the power is a little bit different on these radars, and the radar beam width is different. The phased array has a wider beam. The KUN has a narrow beam, about 1 degree. So keep in mind all these important concepts. Next is weather radar signal sampling. So we have a radar, and then we get time series. How do we get it? What are these time series? Some bunch of numbers, how they are organized. So this is what happens. Radar sends a series of pulses. I'm showing one pulse propagating right now, then it listens to the echoes. The next pulse, and next, and so on. So radar sends a number of pulses, The pulses are sent with pulse repetition time, PRT. This is an important number which determines range, maximum range, and maximum velocity which radar can detect. Then this voltage which is received is sampled at some time, and time series are recorded. In this image, one stick represents an IQ sample. IQ samples means the voltage was sampled with a coherent receiver such that we get two numbers for it, imaginary and real part of this echo voltage. So we have complex time series. So this way we obtain one radial of data, then we have to repeat all the procedure to obtain the whole scan, or how many radials we would like to receive. Now, if we take one range location, we have several samples contributing to this range location. So for one range location, we can compute mean power, mean velocity, and spectral width. And those are generally the numbers which go to the radar display, and that's what we can see when we download images from the website I showed you before. So those will be mean values out of all these samples. This is very important. So you always have to keep in mind that a pixel on a radar display is really not just one come from one sample. It comes from a bunch of samples which been averaged and processed together. So next we will look at the spectrum. How do we obtain a spectrum for this time series? So we're back to this acquisition scheme. So we send pulses, M pulses in this case. We received all this time series data, and we have one radial of data as shown here. Now again, let me reiterate it. It's important. One pixel on the radar display comes from many samples. If this number of samples is large, then we can estimate a Doppler spectrum. We can use different estimation techniques. In this presentation, I'll just use Fourier transform, but we're not limited to that. So here's an example of Doppler spectrum. The axes on this plot are power in decibel on logarithmic scale, and Doppler velocity. So when we estimate the Fourier transform, for example, we have to translate the frequency axis to Doppler velocity. What does this mean? Positive and negative velocities means the motion of the scatterers toward or away from the radar. So back to this picture. Forward or away from the radar would mean positive velocities. Okay? Now, why do we want to do that? Why don't we just want to keep one number on the radar display? Why do I want to look at the Doppler spectrum? By many reasons. And first of those reasons is because Doppler spectrum would show me what is the noise. Here I highlighted with green. It would show me if there is ground clutter, if there is a weather signal. When we computed this pixel on the radar display, we made an assumption that the weather signal is Gaussian and there is nothing else in this resolution volume, just the weather. Well, that is not true in many cases. Sometimes we have multimodal spectrum, meaning that we have many peaks, and when we make an average of that, we don't get really a representation on what is happening with the atmosphere. We get some other signals mixed in. We don't want to do that. We want to, because this is a weather radar, we want to measure weather returns.
Question.
Yes?
What does ground clutter mean?
So the question is, what is ground clutter? Ground clutter for the weather radar are returns from the objects on the ground, towers, buildings, and ground itself. If the radar beam is pointing at low elevation, you can have mountains, hills, road structures.
Those things are irrelevant to weather, so you want to get rid of
Yes,
them.
we want to take care of them. And here is an example how we would like to take care of them. So again, we have the radar beam and resolution volume, and in the same resolution volume we would have a non-moving ground clutter, and we have the moving weather. Again, pay attention, in one resolution volume we have two types of scatterers. We would like to get rid of that hotel or building, but we cannot do that. If we could do that, then our spectrum would show us the velocity, the mean velocity, the spectrum width, and then the area under the curve will tell us the power of this weather.
So what's your criterion for discriminating clutter versus signal?
We'll get to that
Okay,
in a second.
sorry. Okay.
So we go back to the outline. So I gave you the brief description of how the signal is obtained and what we expect to see in the spectrum. Now we're gonna cover the ground clutter filtering. In this section, I will talk about phase-based clutter identification. I'll show you some simulation. I'll present you what spectral fields are and what power spectral fields are. And then I'll give you an example obtained with phased array radar in WRT. And the exciting part, I'll show you the comparison, what would happen if we used the ground clutter filter that is currently used in the system. So we're looking again at our spectrum, phase-based clutter identification. If we go back to time domain, so we have a bunch of samples. I want you to think of them as phasors, because these are complex samples, so they all rotate in phasors. If I'll time index these samples, say take odd index number of samples, and make a spectrum of that, then I take the even samples and make a spectrum of that. So I will get two spectra which would be pretty much very similar. I would have clutter in both of them, which will be identical to my clutter in the original spectrum. I would have weather, which would be somewhat similar to what I had in the original spectrum. Notice that the Doppler velocity interval for this new spectra is shrunk on half. Therefore, I would have some folding. Folding means that this part of the weather will appear in here. So you say, why I'm doing all of this? What is the purpose of all that? Well, I want to identify clutter, and this is how I'll do it. I'll take the samples, complex samples, from each of the spectra, and I'll find the differential phase between the samples. And I have many samples, so I'll take each pair and find differential phase between those. What I'll get is the plot, which will be as a function of Doppler velocity, the plot of differential phases. So the plot of differential phases as a function of Doppler velocities. What does this mean? Well, a little bit later I will tell you what it means. Let's just do some observations on this plot. Notice that at the noisy part of the signal, I have noisy part of the phase. At the clutter part of the signal, I have flat phase. Flat, very close to zero phase. And where I have weather signal, I have a slope. We'll observe that, right? So, yes?
Are you assuming your clutter to be stationary at zero velocity?
So the question is, am I assuming that the clutter is stationary at zero velocity? Yes, that's what I'm assuming, that my clutter is not moving. It is a building or some structure on the ground which is not doing anything relative to the radar.
Are there cases where this assumption gets you in trouble? Cars or traffic?
So the question is, are there cases that this assumption is not right? There are cases when we're looking at, say, the bridge and there are cars and trucks are moving at the bridge, and the bridge is elevated compared to the ground around. In these cases, you cannot discriminate as clutter, and this would not be called a ground clutter. It will be called perhaps a moving ground clutter. So I said now I will explain you what this function is. I called it phi-o, and I just made up this name, so it might be renamed later. Phi-o is a spectral density of phase coherence. Phase coherence is generally a number for one resolution volume. Now we have this number spread out in the Doppler velocity space, therefore it's a spectral density. To contrast it with power spectral density, when we're looking at the Doppler spectrum, it's a power spectral density. In this case, we're looking at a phase spectral density, in phase between even and odd time series samples. So and again, this is more intuitive name for it, differential phase between spectral coefficients of even and odd time series samples. In the second part of the talk, I will present you polarimetric spectral analysis. In polarimetric spectral analysis, we will have two channels to obtain the returns from the scatterers. Will be horizontal and vertical channel. For people who deal with dual polarization data, this differential phase is computed the same way as I compute my function of phase coherence. And when I present it to you, I'll reiterate to you, so we'll keep it in mind. So it's a differential phase between even and odd time series samples. Okay? So I would like to show you some simulations, because all of this was just hypothesis. Now you probably ask me, is this really true? I'm simulating my signal close to the signals. Oh, let me start over. First, I collected data, and then I observed this phenomenon, and then I decided to run simulations and see if it holds. So I did it kind of backwards from what I'm presenting. So therefore, I simulate the data similar to what the data acquisition scheme was. The pulse repetition time is 800 milliseconds. The signal to noise ratio is 20 dB. Clutter to signal ratio is 40 dB. Spectral width, it's the width of my weather, is 2 meters per second, and I simulate the weather velocity moving toward the radar at 10 meters per second. Here is the power spectral density, and I simulate 100 realizations of this signal, and they all overlaid, and you see that they're very similar. There's a little bit of fluctuation in the noise part. So this is 10 meters per second. And this is clutter. Okay? And then I compute this differential phase. It wouldn't let me. And notice, just like I hypothesized, I have noise where the noise is. Noise. Again, I have half of the velocity interval. I have slope where the weather is, and flat where the clutter is. So I zoom in so we all can see that it's really very close to zero. Now when I showed this to my supervisor, he said, well, sure, everything looks nice because our clutter and weather are separated. What happens if they're not separated? Then we will have real trouble. Because with this situation, there are other spectral filters which can deal with this very well. Then I had to simulate different weather velocity and see if it still holds. And this is what the next slide is about. Again, notice that the phase is close to zero at the Doppler velocity is close to zero. Now what I will do is I would show you the different spectra with the weather changing from here 5 meters per second. So I will change the weather in this fashion, and at some point the weather will be overlapping the clutter. And we will see how the phase behaves Is it still staying 0 or not? It's like plane. Let's see what happens. And I zoom in so we can judge how much it changes. And let's observe. I'll play it twice so we can see what's going on. So the velocity is changing, the phase is staying 0 at the coefficient of ground clutter. So let me go back and play it one more time. So notice, it is very close to 0, even when the clutter and weather intersect. It is 0. Actually, the worst case out of this shown is where the clutter and weather intersect due to the folding. Again, let me show, let me point. I'm sorry. Let's go back. Our velocity interval is half the interval. Therefore, this weather velocity folds into clutter. And this is the case when we have some fluctuations in the phase. Now, what I'm doing really in here is I'm computing the width of clutter without computing the value of the width. All I care is how many spectral coefficients represent clutter returns. Why is it important? Because then I can take this phase, apply it back to the power spectral density, and identify precisely the coefficients of clutter. So I'm avoiding this computational clutter width, which will have some loss due to averaging or due to rounding error. And I don't have any water, and my voice is leaving me. So far you saw the separate plots of spectra or overlaid spectra. Let's look at spectral fields. So first the concept, what are the spectral fields? We're back to our data acquisition scheme, and we have a Doppler spectrum. And recall that I said it was at one range location, like that. We have many range locations, so we have many spectra. Now if we color code them and put them all together, then we would have a field of spectra. So we have Doppler velocity here, and we have range here. And the color will represent the power in logarithmic scale. So next I will simulate the clutter and weather with small Doppler velocities. This is the idea. So I have several spectra. My weather will be changing very close to clutter. And here is the spectral field. And this is the simulated spectral field. So clutter is in the middle. Weather is this orange line. And what I want to do is I want to run it through my clutter identification algorithm and see how it finds the clutter. And then I notch it. As soon as it finds, it says the 0 phase means let's notch it so we could see it. And that's what happens. Notch spectral coefficients are precisely the locations of clutter, which is really nice. And this is exactly what I wanted to start with. So next, I will show you the real data. And again, this is the data obtained from phased array radar. And there are some technical issues with the radar at this point, which are being fixed again at this point. The radar cannot collect any data close to the radar. So we start collection from 10 kilometers. The radar has a DC associated with it. It means if I looked at the spectrum, I would always have a peak at 0 velocity. And it's a glitch in the system, and so there's nothing we can do with it. Therefore, we have to do some spectral processing or some signal processing to get rid of it. And here is the filter data. What we see in these images is that white and purple show the clutter. And in this image, the filtered image, the clutter is gone. Now, this is storm. And storm is preserved. So everything looks really nice. And that's what we want. Simple, nice, and it works. Now, here's an example of spectral field in one of those or azimuths, so range locations. The spectral field to the left shows what we have from the phased array radar. So again, as I said, that we have DC, that means we have voltage at all, I'm sorry. Something happened. Give me just 1 second. Maybe like that. 1, 2, 3. Okay. So we have a voltage at 0 Doppler. That's DC. We want to get rid of it. Now you notice that the levels of the power at different range location is different. Somewhere it's higher, somewhere it's lower, which I don't have on my spectra to the right. This is because I used different weighting windows. Hannian, Bachman, Nuttall. Rectangular window is used where the signal is weak. Rectangular window means no window in. So as data comes in, I don't weight it with anything. And now you can see that in the image to the right, the clutter is identified and filtered, and everything is nice, and the weather signal is preserved.
What was the motivation for the windowing?
The motivation for the windowing. So when the radar is obtaining signals, some of the signals can be very strong, some of them can be weak.
Right.
Generally, when the signals are weak, we do not window data. We leave the rectangular window. Next, depending on the strength of the received signal, we have to window data to decouple this spillage of the strong component in the Doppler bins to the weaker ones. Say if we have a very strong power component at 0 velocity, it will generally spill into the neighboring bins. Like at 0 bin we would have power, it will spill at 1 meters per second, 2 meters per second, and so on. When we apply a window, for example, Hannian window or von Hahn window, what happens is that due to the window side lobes, I don't remember exactly what is the ratio between the main and side lobe. It's something like 50 dB, 60 dB. It allows us to decouple the spillage. It allows us to bring these spilled powers back to the main lobe, and then we don't have these streaks on the spectrum as we see it here. Now when your power is really strong, like exceeding 60 dB, you have to use very aggressive windows. For example, Bachman-Nuttall would be the example of a very aggressive window. I think the suppression there between main lobe and side lobe, something in the terms of 90 dB. Why is it bad to use aggressive windows? Well, what happens is, though the window will bring your side lobes down, it would also increase the width of your main lobe. So an aggressive window will have very wide this main lobe area. A less aggressive window will have smaller width, but it will have a smaller difference between your main lobe and the beginning of your side lobes. So what we want to do is we want to use window depending on how much power we have in this range location. Strong power, we want aggressive window. Small power, we want a less aggressive window. And very small power, no window at all.
So you do it in an adaptive fashion?
It is an adaptive fashion, and it entirely depends on what is the power in this range gate. Okay. So this example was for a storm. And again, there are many spectral filters which can deal well in situations with storms because storm has a lot of power into it. What happens in clear data? And this is an example of clear air. Generally, filters cannot deal with clear air because the signals are very weak. And when you filter, everything goes away. This filter which I'm presenting now is doing very good job. Again, on top I'm showing the unfiltered data, and on bottom all this clutter is gone, and the weak 5, 10, and 15 dB signals are preserved. These are very weak signals. When we look at the spectral field, we see that there is clutter. Well, there is DC, obviously, and it's gone after applying this phase-based clutter filter. This is a very good filter because it doesn't remove everything. It removes precisely in the locations where there's zero phase. It's a very narrow, very adaptive filter. Okay? So, I would like to show you more examples, and then I'll motivate you why should we do this filter comparing to the existing filters. So again, first example is the clear case, showing that clutter is there and then clutter is removed. The other two examples are the storms. What I want to point you out here is that the second storm has a slightly different clutter pattern than the first storm. And this happens due to an interesting phenomenon, which I already mentioned you, called ducting or subrefraction. Because we have no way of knowing how our beam propagates, is it going like this or like this? We don't know where the clutter is going to be. At this point, the weather services dealing with clutter have clutter maps. So they generate clutter maps maybe once a week, maybe once a day, depends on how good your radar is. And then they use these clutter maps to say to the radar, okay, here I have clutter, we have to deal with that. And then they apply an iterative filter, which takes this range gate of clutter and then tries to put a Gaussian where the clutter is and does it in an iterative fashion. So it's very slow processing. So here I'm trying to motivate why this new filter is better, because it's simpler. There's a problem of this new filter. The problem is the bandwidth. Because as I told you, I have to compute 3 Fourier transforms per each resolution volume. Then I can argue that the current clutter filter takes a map, which we don't precisely have, or it might be not accurate, like in this case. When the beam does not propagate normally, then our clutter map is not accurate, we will have big, large errors. This will not happen in my case with 3 Fourier transforms and adaptive selection of the clutter. All right, now I will compare these two techniques. I told you that this new technique is good. Now let's see what about the performance. Old versus new spectral filters. I put it old in quotes because it's really current spectral filter. And also there's another argument I need to make. Really, the phased array doesn't have any spectral filters. I had to adapt the spectral filter used currently with by the weather services for the phased array. And there are several issues I had to address by doing that. In the very beginning I told you, well, I'll repeat it again. The phased array is electronically steerable radar, and WRT is mechanically steerable radar. The difference between these is in how wide your clutter is going to be in your spectrum. When the radar is moving, it acquires data while it's moving. Therefore, the clutter would be smeared. It will occupy many Doppler bins. When you look at clutter with the electronically steerable radar, the beam is not moving, it's steered electronically. Therefore, your clutter is going to be narrow compared to the mechanically steerable radar. So therefore, I had to take this filter from which is currently used and adapt it, make the clutter width extremely small, because the filter is model-based. So filter assumes that the clutter is going to be yay wide, and then it makes this Gaussian model, puts it on it, and interpolates and does an iterative fit. Because now our clutter is a lot narrower due to electronically steerable radar, we had to fix this. Now, first I'm showing unfiltered and now filtered. Notice that unfiltered, not like this. Unfiltered and filtered are very similar. It's hard to tell by the eye, but then let's look what happens in the spectral domain. So again, look at spectral fields. And the thing to note here that the new filter removes small number of spectral coefficients when the old filter removes a large number of spectral coefficients. The explanation why this happens, again, because the filter makes a model and assumes that the model is Gaussian, and when you have a strong peak like 80 dB peak and you have to have a Gaussian put onto it, you have to have a support for your Gaussian, and therefore you have this spread of the coefficients, which you can observe in here. Now, let me zoom in so we can all see what happens in real clutter, no clutter. This is old filter, new filter. Notice that new filter recovers a little bit more signal, which is not really a lot. I'm making some scattergrams. I'm taking the signal before filtering and signal after filtering for the old method, and again signal before filtering and after filtering for the new method. And I color code these scattergrams to see where the scattering occurs. And notice that these filters are very similar, so the performance is pretty much the same. Now the question is, a trade-off is between, do we need to have clutter maps? Do we know how our beam propagates? With this case, we don't need to know that. Now, do we have enough bandwidth? Can we compute 3 Fourier transform for each range gate? With this case, we have to have it. How much time do we have? Well, do we want to do iterative fit? Do we want to model our clutter? That means we need to know a priori how wide our clutter is supposed to be. That means we cannot apply it to any radar. We have to do analysis for the radar a priori to our data collection. Then we can use this radar. Okay? Now, I showed you this clutter filter. Now we all are familiar with clutter filtering of two methods, with the old and new one. Now we're going back to outline, and we switch into a completely different topic, which is again spectral analysis for biological scatter identification. In this case, I will not use the phased array radar. I will use the mechanical steerable antenna, which has dual polarization. So the difference here is going to be, we will have 2 channels instead of 1 to obtain our signals. So first I will cover some questions which we need to address, present you again signal sampling for dual pole now, show you power spectral fields in different channels, present you polarimetric spectral densities. This is a hot area of research. Show you the spectral censoring, spectral velocity-azimuth display, and some problems with the old displays. And outline you what are the objects of polarimetric studies. So some questions. When we look at the resolution volume, we might have multiple scatterers in there, and each of them might have their own behavior, their sizes, and their directions. So in this case, we would have wind, bugs, and birds. So birds are moving to migrate, so they have their direction. Wind might be blowing in sort of similar way, but its own way. Say if it's a southwest wind and birds want to go south, they will still use the southwest wind to move. And then there are bugs. Bugs will generally move with the wind because they're small and it's more work for them to oppose the wind. So is there a way to tell when you look at the radar velocity that it comes from multiple scatterers? Or not from something else, from a mix of scatterers? Now, if there is a way to tell it, can we extract this wind velocity? If we can extract the wind velocity, then can we extract the other guy's velocities? Can we tell what are birds doing and what are insects doing? Because some people might want to know that. And the last one is what causes the unusual polarimetric values. I did not tell you anything about polarimetric values, but hopefully from the next slide it will be easy to understand. So we're going back to the weather radar signal sampling, but now we have dual polarization. So signal sampling. Instead of one set of values, mean power, mean velocity, and spectral width for each range, now we have two sets because we have two channels. And therefore, how it's done now, people are trying to use those values to compute three more numbers. That would be differential phase, or the difference in powers between channels in phases. Differential reflectivity, the difference in powers, and correlation between these two channels. And then they make, again, these nice displays, and then they look at them and they try to assess what kind of scatterers we have. Why do they do that? Well, because the primary objective is look at weather. Weather means snow, ice, rain. When particles are falling, they're not round, they're oblate. And therefore, when you look at them with H and V polarization, you can tell by the values of these differential variables what kind of shape those particles have. So you can tell if they're oblate and perhaps they're rain. If they are some irregular shape, they're probably snow particles. The ice would have something else. But we, because we're interested in spectral analysis, we will look at the spectra in those two channels. So now we have two spectra for each resolution volume. And now, for the spectra, we can compute the spectral densities of polarimetric variables. So again, I'm taking one spectral coefficient, one complex spectral coefficient in each pair, and then compute those variables for those two coefficients and plot them as a function of Doppler velocity. And I repeat it for all of them. Now, instead of just these three values, I would have three distributions in terms of Doppler velocities. Why do I want to do that? Well, because these distributions would tell me what is going on in there. Do I have high correlation? Do I have multimodal spectrum? Do I have what kind of values in there I have? Okay. Well, where is it useful? It's useful in echo classification algorithm. And here are three plots I pulled up from the website with JPOL experiment, where they were trying to classify the echoes. And they used reflectivity, differential reflectivity, and correlation between two channels to do that. And on the bottom, there's the classification result. And the result shows you that the gray shows that you have a mix of weather, birds, and insects. Green and yellow show that you have heavy precipitation and hail. And I need to tell you that this case was done in the clear conditions. There was no precipitation, there was no hail. And pretty much without even taking any variables, we can tell that there is always weather, insects, and birds in the atmosphere. So this classification is not very good. So we have problems. They need to be resolved. And again, why they have problems? Well, because perhaps the spectrum was bimodal or multimodal, meaning that you have several peaks, like that. And therefore, when they compute their differential phase, differential reflectivity, and copolar correlation, and they compute the mean of this, it does not represent neither of the scatterers, which is not good, because we want a full and good representation. So, perhaps it would be better if they computed it for just this part, or this part, so depending on what we're looking at. And then we would have a good classifier which will say, those are only insects, or those are only birds, and this is the weather. Because all of them will have special set of values, polarimetric values, because they have different shape properties, different oblateness. So somebody needs to study the scatterers attributes to prove the classification, and this is the tool to do that. And here's an example from the real life, from the radar. I'm showing you two spectral fields from horizontal and vertical channels. And what you can see on these fields that they're not filtered, the clutter is there. I left everything as it comes in. And then there is a signal. If you look at the signal, you notice that there are two bands in the signal. One band is actually coming from the insects moving with the wind. and another band is from birds. So if we compute polarimetric spectral densities, just like I described to you, let me repeat it again. We take one sample from here and one sample from here and compute polarimetric variable, and so on. For each pair of samples we compute polarimetric variable, we get a distribution. Then we would get something like this. I'm just repeating these spectral fields of power on top, and then I present differential reflectivity spectral field, correlation spectral field, and phase spectral field. When you look at these fields, they're very noisy, and you say, what can we get from that? Well, we can average these fields. And in this example, I'm averaging between 30 and 70 kilometers to see what kind of scatterers are there present. And we can make a special new display, which called spectral velocity-azimuth display. In the next slide, I will tell you what velocity-azimuth display is and why there are problems with it. The point is that if we do it from the spectral fields and we compute this spectral velocity-azimuth display, that we could get the tracks of the whatever scatterers are there because we have distributions of velocities. And in this particular case, I have two sinusoids, which means there are two type of scatterers are moving. And the studies showed that those two types were insects and birds. And this deduction came from the differential reflectivity fields because it is well documented that differential reflectivity of insects is larger than that of birds, and therefore we could find which sinusoid belongs to what. Why do we care about those sinusoids? Well, a little bit later, not in this slide, in the next slide I will tell you about VADs again. Before that, I want to say that we also can perform a spectral filtering or spectral censoring, meaning we can take all the spectral coefficients that correspond to noise and just get rid of them. Then we'll clean up our spectral fields, and here's an example of that. So I'll switch back and forth. Those are the cleaned up spectral fields. This way we can pull out the weak signals which are hidden in the spectral noise and expose them. So let me do it again. Please pay attention to the differential reflectivity field. Here you see only one band. After spectral filtering, there's two. So the bird band pops out. It's important for the weak signals. If you're dealing with weak signals, it's always good to censor the spectrum. And here's again example of spectral velocity-azimuth displays which can pull out weather out of this mess. Applying different techniques, I can average spectra, or just take one spectra, I will get different velocity-azimuth displays. Notice that in the previous slide I showed you two sinusoids. Here you still kind of guess there are two sinusoids, but after 20 median spectra, we left only with the weather sinusoid. And this is our goal because this is a weather radar. If we wanted to pull out the direction of the birds, we would have to do some different processing, but we still can pull it out because we have all information preserved. And now I'll explain you what VAD is, because if you don't know what it is, you're probably asking, what is that we're doing here? Well, again, in this example, I was trying to pull out the velocity of weather, and therefore I can start with this contaminated velocity field and clean it up with good velocities representing only weather and nothing else. Here, going back to the VAD, why it is and why do we want it. So first I need to tell you how it's done now. Nowadays, all the radars are calibrated, meaning we compute the noise before we start transmission. And to calibrate it, we just lift the radar dish and look up and collect the data. And whatever we get, we average and say that's the noise. Then we apply it to each range gate to see what is our signal-to-noise ratio. Because now we have the value for the noise, we can say how strong our signal is. After we apply that, we can censor the data and say, if the signal-to-noise ratio is small, I don't want to look at it. It's too small. Now, there is a technique called velocity-azimuth display. This technique is actually, this is the example of velocity-azimuth display. So we have velocity axis and we have azimuth axis. So what we want to do is we want to find the direction of the wind and the speed of the wind. And from the sinusoid, we can see that the direction is where the peak is, and the speed is where they are, again, where the peak is. The problem comes from the next. So we just censored the data because lots of places had small signal-to-noise ratio. We censored it. We end up with this set of data, which doesn't have many points in it. Now, if we take this 30 kilometers range and say we want to take these points and create this velocity-azimuth display, some of these points might be actually coming from different scatterers, from wind, from insects, from birds. Therefore, when we take these values of mean velocities and put them on this velocity-azimuth display and make this fit to create a sinusoid, we really could have very large errors. And so we don't want to do that. Therefore, when I showed you the spectral velocity-azimuth display, this is not going to happen because we have only the distributions instead of mean values. So clear censoring may result in very sparsely filled radar displays, and there is no guarantee that presumably good data is good. With the spectral velocity-azimuth displays, we can tell for sure which is good and which is not. So, I'm showing you an example of polarimetric weather radar data, which was collected for one day, for one evening, from 6 to 11 p.m. And I'm just showing for the top of each hour. The goal is here to show you the clear returns where there is insects, birds, and weather. When meteorologist looks at this data, and this data is not censored because I want to expose all the weather and all the information which is in there. When meteorologist looks at this data, they say, this is just garbage to me. I cannot use it because it's very contaminated, so there is nothing I can do about it. So they have to throw it away. On the bottom, I'm showing why they say that. Because I have wind, insects, actually two types of insects, and birds, all mixed up in each resolution volume. And the arrows actually represent the general direction of the motion. So how did I get these values? Well, because I used polarimetric spectral analysis. So I could analyze the data and say what was going on. I could even censor it. I'm not going to show you the examples of censoring. This is just to get a general feel where we're going and what we want to try to do. For the same case, I'm showing you the spectral densities or spectral fields. These are the censored spectral fields. Please notice that, again, data changes 6, 7 p.m., 8 p.m. I said that I'm showing it on the top of each hour. Notice, like at 6 p.m., there's one band. And in the evening, there are two bands. So therefore, this indicates that in the evening, there was something else going on in the atmosphere. If I look at polarimetric spectral fields, then for these bands, I would have values of differential reflectivity, correlation, and phase. And from the values, like see colors, colors represent the values. I can tell what kind of scatterers are there. Are those insects, birds, or what? So let me flip back and forth. And these are the displays which let us estimate what kind of scatterers are there. And I'm trying to go forward, and I went too far. This is just an example how you can construct a histogram from these displays and then assess what values, what group of scatterers would have, from which you can create new velocity-azimuth displays having multiple sinusoids for multiple motions and for multiple scatterers in it. And then you can go back to a meteorologist and tell them, here at 6 and 7 o'clock you had good data, you can trust it, you can do your numerical models and produce your weather forecast from that. Or you can tell them at 11 and 10 p.m. you had bad data, you can't really use it, you have to use the special techniques to clean it up, and only after that you can put it in numerical models and make the forecasts and whatever you're doing. So we finished with topic number 2, how we're in time. Can we cover topic 3?
You have 3 minutes.
All right, then we won't cover it. All I wanted to say that the first one I showed you the spectral analysis for the phased array. Second, I showed you the spectral analysis for polarimetric radar. So we had 2 channels. And third one, I wanted to show you what do you do when you have non-uniformly spaced data. The whole point of the talk is that spectral analysis reveals hidden features in the data. You cannot tell what is behind the number, but you can tell what is behind the distribution. So you have to do spectral analysis in order to study your data for the research purposes. Then you can develop algorithm which will refine existing techniques and then will spit out nice cleaned up data which represent whatever people want. Well, do you have any questions?
Yes.
Going back to the ground clutter filtering, with the comparing
Can you speak into that little?
I'll repeat his question.
Okay. Going back to the ground clutter filtering, the new method that you have proposed using the model to I guess dynamically change with the ground clutter.
The question is going back to ground clutter filtering to numerical model.
Yeah. So, if you want to use the radar operationally, how fast can you run this model to clean out the data? Because I mean, if you're producing like a severe thunderstorm forecast,
right, and
you have to wait a couple more minutes.
The question is how fast can you use the ground clutter filter?
You said you're doing a couple Fourier transforms that can be
time-consuming. I can answer this question. Currently, weather services uses a spectral filter, meaning you have a map of clutter, and then this map tells you where you have to filter.
Right.
The filter goes in there, and you still use Fourier transforms to filter. Okay. You still use Fourier transforms to weight data. So currently, all data is weighted or adaptively weighted. So there's a lot of processing going on to create those mean values. Now, iterative process is used currently. That's not what I proposed. Okay. Currently, the flagged by the map data is going to the spectral domain and being processed. And this is how they process it. You take this spectrum, then you rank order statistic it. So you order it, the spectral coefficients from descending to ascending. Then you decide where your noise is and decide where you might have clutter. Then you put a Gaussian fit on where you think the clutter is, and you generally start with 2 spectral coefficients. Then you increase it, and you keep fitting the model, saying, did it fit? Did I get rid of clutter? And it keeps doing it iteratively until it decides to stop, until it tells it you went too far, you're covering half of the interval, you cannot go any far. Now, so it is already time-consuming, and it is already required Fourier transform. What I'm proposing is actually takes less time, but it takes more bandwidth. Meaning, before you had to compute only 1 spectrum per range location. Now you would have to compute 3. So you take your time series data, you compute original spectrum, then you split your data on 2 pipelines, even and odds, and compute spectra for those. Meaning now you have 3 spectra. So the question is, bandwidth versus time. Time-wise, it's faster. Bandwidth-wise, there's a problem. Does this answer your question?
Thank you.
Following up on ground filtering.
I'm trying to go up, and it takes so long. If somebody could help me how to go back to the...
That's fine. If I
to exit it. Or maybe I should just use this and exit it.
Yeah, just use the link.
Keep going, ask your question,
Okay.
I'm listening.
Okay, so if I understand correctly, anything taking place at zero velocity has no differential phase information, be it clutter or weather. Is that true?
Yes, this is how it works. Actually, the difference lies in the spectral width. If your spectral width is narrow, the differential phase is close to zero when you're at zero velocity. Weather never has close to zero spectral width. It's always wide. It's actually, at this point, weather services considers 4 meters per second is the weather. Therefore, when you look at this differential phase, it will always have a slope. If your mean velocity is at zero, maybe I should just draw. That would be probably the easiest way instead of going back. I'll draw here. So we're looking at Doppler spectrum. We have zero velocity minus v, v. Your weather velocity is zero here. So this is the power spectrum. So in the phase, what you would have is, again, minus v, va, 0. You would have a slope which will be going like this. And then you would have noise everywhere else. Okay? Just like as you had noise in here. So if you have clutter, clutter has a narrow spectral width. So let's put the clutter on top of this. What happens is that because of this narrow spectral width, this phase difference produced by a clutter is going to be very small. So you would have a little flat in here. That is where the difference lies. So this slope actually corresponds, you can translate this phase into velocity. In that way, you would have a plot of velocity in terms of Doppler velocity. So now, if this was velocity, therefore you have a slope, meaning if you have 5 meters per second, and here it will be 5 meters per second. But for that, you need to translate this phase into velocity. And therefore, you always will have a slope. Okay? It doesn't happen with clutter because, because it's very narrow, and therefore there is no change.
But still, I guess my main question is, if you notch everything taking place at zero velocity, couldn't you have slow weather waves that you would be notching out as well?
Yes, the question is, if you notch everything at zero velocity, could you have slow weather which you'll be notching? This is a very good question, and this is correct. You will be notching a little part of weather, because statistically there is always something which will be at zero velocity with the slope. Yes, but it will be very small number, maybe 1 or 2 spectral coefficients. Now, in this analysis what I showed you, I used notch on purpose because I wanted to monitor how much I filter. Because if I use interpolation, I wouldn't be able to tell. In real life, you would always interpolate where you notched. So you would either make it equal to the noise level, or you would just put a linear interpolation or a Gaussian interpolation. And therefore, if I notch this little one, if I didn't have this, but statistically this point happened to be having zero phase, and you notched it, you can interpolate it and you didn't lose anything. This is an excellent question.
Any other questions? I have a question. So you don't, in practice, you don't really compute this in real time, right?
No, this is a research radar. This is for research purposes
No, but
only.
in general, I'm speaking in practice.
In general.
Yeah, in other words, the people who actually monitor the weather and things, do they do?
People who actually monitor weather, they're too busy monitoring weather. They cannot do any spectral analysis or signal processing. They have to have products to monitor weather.
I understand that, but the products, what do they do? I mean, do they do this in real time, or do they gather the data and then they analyze it?
I cannot answer you this question because I really don't know.
Okay.
I believe that there is some processing done in real time, because this filter, which I'm saying, the old or current filter, is done in real time. So there is spectral analysis going on in real time. But to which extent, I do not know.
I think it's very limited just because of, just the time frame, any minute or any second you can gain. Being an operational meteorologist, can make a big difference.
Yes, but we have such powerful machines now, and when you make them on pipeline and working on in parallel, it's really fast. Things happen like really fast.
I think it's on the order of minutes
Minutes?
away from real time.
This is the national, which is like
in actual use today, it's minutes.
it's like in Florida, right? It's somewhere in Florida.
All over, anywhere that's using Doppler.
So the comment is that people think that it's done in minutes, in the order of minutes in Doppler radar.
Right, like, so if you see something on TV today, it's minutes old as opposed to half an hour,
Okay.
an hour.
So that's pretty real time, actually.
Yeah.
But again, all these techniques which I showed you are not going to be used of operational radars. They're done for the research purposes only, so we could improve the techniques which we would put on operational radars for
So you hope
operation.
they'll make it into the operational radar, right?
Well, actually, we had a meeting just on Friday deciding, and we put some people to do the independent evaluation of this filter, and if it goes through, then it would be operational.
Any other questions? Well, if not, let's thank our speaker.
Thank you.
Very good. That was very informative. I didn't know anything about weather radar.